Who of you has ever wished to move an object through your thoughts? Imagine you are sitting on a couch and you want your remote control to come to you. So this would be very nice. And so imagine if we could control the world around us with our brain waves. This is the promise of brain-computer interface that wants to make bridges between our mind and our external world. Now, the example I did might seem fun, fancy, futuristic for most of us, but there are parts of the population for whom this technology could be life-changing. In the world, we have many people affected by neurological conditions that experience heavily motor dysfunctions. So consider, for example, people affected by multiple sclerosis. And globally, we have more than 2.8 million of individuals suffering of this disease. And yet, most of them retain the ability to move their eyes. So we have this small window of control. We can use these eye movements to enable them to restore the communication between their mind and the external world. And that's why brain-computer interface at the beginning started with assistive applications. Now it's evolving also with gaming applications and much more. But the very first purpose was assisting people. And obviously, we have many challenges in assisting people because they struggle with interacting with the external world, but also with the technology. Because many times, the person has to adapt to the system rather than the opposite. And moreover, it's very difficult to grab these signals accurately, to process them in a real-time way efficiently. So there are very many challenges to be faced. We already have commercially many solutions, and we can divide them into main categories. On one side, we have invasive solutions, and I'm quite sure that many of you already know the Neuralink project by Elon Musk, but there are also BrainGate, Synchron, and on the other side, we have non-invasive techniques, such as Emotiv, Neuralink, Muse, OpenBCI. On one side, the invasive techniques require a surgical procedure to install these devices into your brain. So you can imagine that they are not for everyone, that are designed for specific use cases, and they are very expensive, so they cannot be, they are not affordable for everyone, but they are very precise, they have high accuracy, and they can be used for complex tasks, such as control a robotic arm in real time. And, but they pose also some ethical questions, because Elon Musk, for example, wants to use Neuralink in a first phase just for medical application, but then his purpose is to cognitive augment our brain. So let's talk about this. Maybe we have some ethical concerns. And on the other side, we have non-invasive techniques, and obviously they are much less accurate than the invasive systems. They are not working in real time, but they are cheap. They are very easy to use. And with this work that I'm going to present you, we want somehow to fill this gap, because we would like to have a real-time system working on a cheap device. And this is our aim. And for the time being, we are working on non-invasive system, and we are focusing on a gaming application, but our aim is to possibly exploit it on assistive device. These are the main limitations of non-invasive BCI systems up to now. Most of the processing is happening outside the board. So you have a very limited processing happening on board. Most of it is happening on a PC or on the cloud. And moreover, they have very limited real-time performances, and they target very narrow applications, and that are related to mindfulness, meditations. They analyze the brain waves. We started our approach with we started our technique at the beginning using the helmet from OpenBCI, and I can assure you that it is quite uncomfortable because it has some pins that are in your forehead, so it's not so comfort. And, but now we are switching to use our biosensor developed by ST together with an STM32 microcontroller where the whole processing happens. So the advantage of this system with respect to what is available in the market is that it runs completely on an edge device, and it runs in real time, as I will show you later. But let's go into the details of the system. So our project is composed by a biosensor developed by ST, then a microcontroller, STM32H7, that runs the whole process, and then the final command is sent to a PC for a gaming application that I will show you later on a video. But what's the principle of the biosensor? It is based on the electrostatic charge sensing principle. So when we have an object, it is usually neutral from the electrostatic standpoint because its number of electrons equals its number of protons. But when they touch and then separate, there are the electrons that move from one object to another one. And these are electrostatic charge that create fluctuations in the electric field. So this sensor, this biosensor, measure this change, and it uses electrodes to feel this change in the electric field and an electronic circuit to amplify and process the signal. How we used these electrons, okay, this is one of my colleagues that volunteered for this task, and we exploited the different configuration for the electrodes, and but we decided to use the eye movements because, as I already said, many people retain the possibility to move the eyes, and also we decided to use this configuration because we could exploit it in wearable glasses. Because we exploited also other configurations that could be suitable for visors. And sometimes they are most effective, but at this time we are targeting wearable glasses, so we decided to put the electrodes on the nose, and the electrodes behind the ear is as a reference. We collected the data set using with the 9 people, and we decided to grab 4 different classes. The first one is involuntary blink, but just because we want to discard it, because we don't want to control anything with our involuntary action. Then there is the voluntary blink that can be used like a click of the mouse. And then we have looking right and looking left. I mean, we are looking to the center, then we look right and come back without moving the head. This is quite challenging. And then look left and come back. And then we designed a completely software pipeline. We started, obviously, designing the whole system on the PC, and then we deployed it on the firmware on our microcontroller. And this pipeline is composed by different blocks that I'm going to explain in details. The first block is a preprocessing one. Then we have in parallel a data collection block and an event detection. And finally, we have an event classification that is based on a one-dimensional convolutional neural network. The final class that is recognized is sent via USART to the PC for controlling the game. So why the preprocessing? Because data are quite noisy. And we are using 3 different filters for preprocessing the signal. First of all, we are using an high-pass filter to remove the DC component. Then we are using a notch filter to remove the frequency around 50 Hertz to remove the power supply's frequency. And finally, we are using a low-pass filter with a cutoff frequency of 2 Hertz for removing extra noise that is in harmonic at higher frequencies. And here there is an example of raw signals on the left, before any processing, any pre-processing. And on the right, you can see the effect of applying these filters to the signals. So you can see that the signal is centered around the 0, and moreover, it's much less affected by noise. And this is helpful to have also a small neural network after, because the neural network doesn't have to learn the noise, so can learn directly the cleaned signal. After this pass, we have an event detection. We could have used directly a temporal convolutional network for processing directly the signal, but it would have been always on. We decided to have a very simple algorithm always on, that is this event detection, and then it activates the neural network for the processing only when there is a relevant signal. And this event detector is based on Z-score. It is a well-known solution. We didn't invent anything here. And Z-score tells you how far is your signal from the average in terms of standard deviations. And consider that in this example, okay, maybe it is visible. Okay, here. The event detection doesn't recognize perfectly the peak. Because, where is the point? Okay, the peak. It recognizes, for example, this part. This is because it is working in real time. So we don't have the whole signal. In this moment, we have just this part of the signal. So the Z-score doesn't know that the signal is going to grow. But this is sufficient to understand that something is happening, something different than the normal behavior. So when we detect this event, we collect 100 samples before and 200 samples before, for a total of 300 samples. And consider that in the firmware implementation, these 100 samples are already grabbed because we have implemented a FIFO mechanism. Okay, after that, we have a very, very simple neural network. It is composed by very common layers, convolution, max pooling, ReLU, softmax. And as you can see, its input is 300 because it is the size of our window, by 2 because we have 2 channels. And the results we gained on this limited data set are quite promising, because we obtained about the 90% of accuracy using a k-fold cross-validation procedure, and the flash is just 18 kilobytes, the RAM 6 kilobytes. And the more interesting part is that this CNN runs in just 0.76 milliseconds. But we need much more time to grab the signal, because we have 300 samples at 240 hertz. That means 1.25 seconds to collect the window and 0.75 milliseconds to execute the network. So it is real time. And now I can show you the demo. Okay, so here we have again Vincenzo, my colleague, that is wearing these electrodes, and he will command this video game. So when he looks here, you can see the commands that is identified. When he voluntarily blink, the car jumps to avoid the obstacle. And when he look right, the car moves right, hopefully, if it is correctly understood. And the purpose is to get the ST coins along the way. So let's see. Okay, he did. The score here is incrementing. Okay, so this was just a fun application, but to understand if the system is working. Now our aim is to embed this system in wearable glasses and to make real-time testing, to receive also feedback, because we saw also that brain waves and also electrooculography can vary from one person to another. So we need to explore also some system of personalization. So maybe a calibration procedure would be needed to adjust the weights of the network. But yes, we are in this process of exploring more, and yes, we would like also to expand the functionalities. Thank you.